Okay, in this lesson we're just going to review the concept of composition of functions. So what was composition of functions? Well, it was the process of forming a new function by combining two simpler functions in a simple way. Really what we're interested in being able to do is to do the opposite, to take a complicated function and be able to view it as simpler functions that have been combined together through composition. So first, let's just see how this all fits into what we've been doing up until now. We have been learning a bunch of rules to take derivatives, okay? And the functions that we've been taking the derivatives of have been getting ever more complicated. And how have we taken the derivatives of these functions? Well, at the very beginning, we learned a few basic rules, and we learned how to think of our more complicated functions as a combination of simple functions, and then apply the rules one by one. So when we were looking at a function like f at x equals 5x to the power of 4, we said, oh, this thing over here, you can use the power rule to do the x to the power of 4, and then you can think of this as x to the power of 4 times a constant, and then you can use that constant rule. If we had something like y equals x to the 7 minus 2x squared plus 5x, well, we knew we could do the derivatives of each one of these terms separately, and then combine them together using the addition and the subtraction rule. When we had something like this, we said, okay, we've got two functions multiplied together. This is our one function. This is our other function. We're going to do the derivatives of those functions separately and combine them together using the product rule. Finally, if we had a function like this, we said, oh, we can do the derivative of the numerator separately from the denominator, and then combine them together using the quotient rule. So we have gradually worked our way through a number of different methods of combining functions together through these rules to approach ever more complicated functions. So that's what we're going to do today as well. Or in this unit, what we're going to do is we're going to look at complicated functions that can only be thought of not as by adding, subtracting, multiplying, or dividing functions, but by doing composition of functions. So what was composition of functions? Well, let's say we are given two functions. F at x equals 5x plus 1 and g at x equals x squared. To do the composition of these functions, we use the notation FOG of x, or the notation that I like better is f at g at x. And I think this second notation really gets across what composition actually is. We are taking one function and we are subbing it into the other function where we see x. So if our outer function f here is 5x plus 1, we can imagine subbing that function g at x in where we see x in that other function. So this would become 5x squared plus 1. Now the order was important when we did this. If we instead did GOF of x, then we are taking our function f at x and we're subbing it into our function g at x. And these didn't necessarily work out to be the same thing. So if I take my function g, put a big space anywhere I see x, would look kind of like that, and then I just want to sub my function f, which is 5x plus 1, in there. So I get 5x plus 1 all squared. So notice, again, they don't work out to the same thing. So the order is important when we do this composition here. So let's just do one more example here of composition. Let's say our functions are f at x equals root x squared plus 49, and g at x is equal to x to the power of 4. Let's find f at g at x and g at f at x. So what is f at g at x going to be? Who wants to take a shot at this one? Malcolm? Okay. So we'll just, yeah, plus 49. And we put the x to the 4 in there. Good. And then, as Malcolm said, we've got a power to another power. So we can just write this as x to the power of 8 plus 49. And then what do we do with this square root now that we have it? Can we simplify this any further? Marine. All to the power of 1 over 2? Okay, so we're just rewriting the square root as an exponent? Okay. Can we evaluate that square root is what I'm asking. Sorry? Yeah? You think so? Who thinks we can evaluate the square root? Let's see a show of hands. Who thinks we can't? So after much discussion, we decided that no, this was not mathematically valid, that you cannot apply that square root to these two terms separately if these terms are added together. So we would just leave our expression there like that. Okay, what were we doing when we were interrupted by all of that math? We were doing composition of functions. So let's try doing g at f at x this time. Who wants to tackle the composition of these two functions? All right, well, let's see. Our outer function is going to be that g at x, so we're going to have something to the power of 4 here. What is going to be to the power of 4? It's whatever we have subbed inside of g at x, which is our function f at x. So that's going to be the square root of x squared plus 49. And there's our composition. Same question I asked before. Can we simplify this? What do you think? Riley? That is the question, isn't it? Can we make this x squared plus 49 to the power of 2? What do we think?
Yes.
Why do you say yes, Liam?
It's basically x squared plus 49 multiplied by x squared plus 49. It's a complex function.
Yeah, this is all fine and good. Yeah, we can do this. And so McKenna isn't confused anymore. We'll put this in black. Yeah. All right. What is it? Yeah, just like that. Okay. So we can think of that square root as to the power of 1/2. Multiply our two exponents together. 4 times 1/2 just gives us 2. And because that square root applies to everything in these brackets here, we're okay because both of those exponents apply to the entire x squared plus 49. Okay, so that's composition of functions. What we want to be able to do is do the opposite. Take something that is complicated and think of it as being made up of two separate functions. So here I've got a function h at x equals x squared plus 2x plus 1 squared. I want to think of h at x as being composed of two functions, f at x and g at x, and I've combined them by composition, f at g at x. What should my two functions be? And here I might even color code them here. G at x and f at x. Well, if I look at how I could break this apart, I could take this entire thing in here inside the brackets and think of it as one function. So g at x would be x squared plus 2x plus 1. Then how did I get h at x? Well, I took g at x and I subbed it inside another function, f at x. What would f at x have to be? Well, it would have to be sort of just this part to the power of 2. So that would be like x to the power of 2. So if I do that composition and I take g at x and I sub it into f at x, I would get x squared plus 2x plus 1 all to the power of 2. So let's try this again, something a little bit more complicated. I've got another function, h at x, 1 over the cube root of x squared plus 7. I want to think of h at x as being made up of two functions that have been combined using composition, f at g at x. And I want to figure out what these two functions, f at x and g at x, should be. To do this one, I would start off by rewriting h at x. How can I rewrite that to make it, put it in a form that's a little bit easier to manage? I got a cube root. It's down in the denominator. What can I do with that cube root? Yeah. Yeah. X squared plus 7 to the negative 1 over 3. That cube root is really an exponent of 1/3. If it's down in the denominator, I can bring it up to the numerator and make it negative. Okay, so looking at x squared plus 9 to the negative 1/3, what is our inner function, or g at x, and what is our outer function, f at x, that g at x has been subbed into? So what's the inner part of this thing, do you think? Right. X squared plus 7. Yeah, this thing right in here is going to be our g at x. What then is this function that g at x has been subbed into, our outer function f at x? Well, it's the part that's left over. It's going to be x to the negative 1/3. And that is composition of functions and the opposite of composition of functions. The whole